Ba-dum.
Hi,
Hello.
we're back.
We're back. It's 2020.
2020.
Same show, new year. Nothing changes.
Same year, new show? No,
No.
other way around.
Yeah.
There you
I'm
go.
still dumb. You're still smart. How's it going?
I'm good.
Yeah.
You good?
Yeah.
How's the year treating you?
It's pretty good so far.
Yeah.
I mean, basically just the same as the end of last year. Still playing too many video games.
Video games, man. Video games.
Good stuff though.
Yeah.
Yeah. We're taking a little bit of a break from. Actually, I don't know if I would call it fully a break because nothing's really slowed down for us.
No, it was 2 extra weeks.
But we just needed to. I meant like for content for like NGON.
Yeah.
Because we stopped doing videos for a little bit.
Mm-hmm.
But we didn't really stop doing videos because we're still making videos for next month. It's just that we didn't have time to prepare all the videos in January because we had less time in December.
We had all the stuff. It was just we paused it for like 2 weeks and then could just continue on.
Yeah. I blame Ella and George. They went on vacation.
No blame.
Unacceptable.
No blame.
I blame. Yeah.
Shall we get to it?
I guess.
There you go. So today will be kind of so what I wanted to do is I wanted to go into kind of a big topic in programming that we haven't touched either in season 1 and in season 2. So this is a completely new thing that we're going to do. And since it's a big topic and it's kind of tricky to go into, I'm going to split it into 2 episodes. So it's going to be this episode, which is going to be more of a presentation style episode. I don't think we'll be doing any coding. Depends on how long this will take. And then in the next episode, we'll be doing the same topic, but we're doing it more practically. So we'll be playing with it. So fun times today. There's no homework. Yeah, because there will be more homework next time.
Oh no.
Yeah.
But that's a problem for future me and future everyone else. Whatever. Yeah, I don't. Me right now, we're good.
We're good. But again, the big thing with programming is that you need to practice. You need to be like you've had a month now of playing around. So yeah.
I watched those videos.
Mm-hmm. Yeah.
A lot of what he said was like I got some of it, but some I think just as I'm talking about the homework from the previous episode, which was to watch a few videos, and I understood the concepts of what he was talking about, but then he started using phrases that I never heard. Oh. It was mostly related to like the functions and like the variables that he was adding in, and that's where I was like trying to understand those while trying to understand what he was doing on the screen, and I was like,
yeah. There is some terminology that like I've tried to keep the terminology the same throughout, even though in many aspects, like a function is sometimes called a method. Oh. For example, that's a method is just a function. It's a function in a class. Oh. So there are different words. So I've sometimes kept it a little bit more simple just to keep it consistent throughout. That's why also I talked about earlier, it's important to learn from many people because they might talk about a thing differently.
No, I only want to learn from one person.
No. Okay. So last episode, we looked at project structure. We saw that we could include files and we could have code all over the place. And the big thing was that we could split out the definition of the function. So we could have like the header of the function in one file, and then the actual the implementation of the function in another file.
It made one file that actually technically did everything look real simple, and then everything else was super complicated.
Yeah. So you could just say like, hey, use this file and everything is happy. This week, we're going to go a bit more low level. And there's a reason for that, because I think knowing about this subject in a low level sense will help you. I think knowing about it in a low level sense is better when you start using this concept or this idea. So this might be a little tricky to learn a bit low level, but I think if you have that in your bag when you're learning about the actual memory problem that we have, it's better, basically. So we're going to look at memory and data, basically.
Just adjusting my chair slightly.
Yeah.
It's a bit leaned forward. I feel like I'm going to hit my face on the desk at any moment. Just dunk.
Okay. So, ready?
I am.
Good. Because there's one thing that we haven't done yet. Hi, Gabe.
Okay.
We need to talk.
Oh, no. Oh, no. Who's going to take the cat?
So we need to step things up now. We've learned a lot. We've learned many of the core fundamentals. So as a way of, since we've been in a break and it's good to recap, here's a review.
Nice.
So just to go over, because I went over all the last episodes, or the 5 episodes that we've done variables. So if we need data, we store it in a variable. That's where it is. If we need to do things, but only sometimes, we ask the variables questions, which is conditions. And then variables have a specific lifetime, a scope. So we create the variable inside of some sort of curly brace. They live there. When the curly brace exits, that's it. Variable is gone. So, example. Here's a health variable, 100 health, kind of with the theme that we've been doing recently. Cool. So, if we have functions, if we have code, sorry, I read the if we have and then went up. If we have code that we want to use again and again, we can create functions. Like, hey, this is a common bit of code that we want to do again and again. We can create a function. Functions can call other functions. So we can have a chain of this. And functions can take in and return all sorts of data. We played with all sorts of variables. And we even found out that if we create a class, we can actually take in the class and we can return the class. So that's not limited to that.
And all the functions we were doing with all the int, bool, and char.
Yeah. So instead
void.
of so that's the type here. It's a heal.
Yeah.
Taking a health and how much you're healing for, and that int can be a player, for example, or you can return a player, for example. So if we need to do things many times, we have loops.
Yay!
Great. Loops are basically if statements that keep running while they're true. So you can think of it as an if that just keeps asking the question.
And there was a few different types of loops.
Yeah, there's a while loop and the for loop.
Yeah.
And there are 2 types of for loops. You can either you can create variables in the for loop, or you can do a for loop through a container. That's basically those. And we looked at the while loop in our example. Java, no, we're gonna do C++. So that's that. And then classes, if data and code are used together a lot, we can group them in a class. This can allow us to create a nice interface on top of a more complicated underlying system. So here, for example, we have a player, health and damage, player. Cool. Great. That's it. That's the 5 episodes.
There we go. We did it.
That's what we've been covering in the first 5 episodes. So there's a common theme here of, we go here, for example, with the functions, that the function take in data and they return the data, and us creating variables on the stack, and that the variables have a specific lifetime. So that's the thing we're going to look at today. We looked at project structure. If code is independent and reusable, we can place it in another file and then include the file anywhere in our projects. And we can split the interface of the code and the implementation into 2 files, a header file and a CPP file. Yeah, here we go. Now, here we go. Yeah, so we have the player H file, which actually defines the player class, and then we can use the player class. Okay, so let's look at a function like this. So a function like this looks pretty simple. It's called take damage, takes in 2 variables, health and damage. And I'm doing things in a very specific way. Like I could do it differently, but I'm going to do it like this. I can create a new health variable. I assign it to the same value as health. I subtract damage from it, and then I return the new health, right? So I'm returning an int, taking 2 arguments. So this seems pretty straightforward, right?
I'm calling it new health just to differentiate from health itself.
Yeah, it will be more clear later on why I'm doing it. I'm just doing it for an example. I could say, I could use this thing here. I could take this health and reduce it by damage and then return this one again.
Yeah.
But I'm making a new one as an example case.
Thank you, Volga RS.
Thank you. Okay, so yeah. And then anybody can use this function. You give it a health, you give it a damage. It will do the calculation for you. What's important for today is that we don't care that much about what the code is doing. We only care about what memory we have and where. All right?
Okay.
Great. So, what is known? And that's the main question. What do we know? How many variables are in this function? So how many would you think?
2.
2?
Health and damage.
Health and damage.
Well, there's new health.
So 3,
Yeah.
new health. So we have health and damage coming in from the outside.
Yeah.
And we have...
But then we're creating new health.
Creating new health within the function.
Yeah.
Cool. So someone else gave us the health and damage, and that's fine. Or they gave us the value of health and damage. That variable is still created within that function. And we ourselves create new health, do something with it, and return it. Okay, so 3. There's actually 4.
Take damage?
No, the return value.
That's not the same as new health?
No.
Okay.
No, not in this sense. So new health is a variable. The return value, you can also think of as a variable.
But is that technically because the return health is returning that value to something else?
Yes.
And only the things within the scope are relevant?
So on line 3, we create new health.
Yeah.
And that's a variable. We created there. Great. And then on line 6, we're returning new health. We're not actually returning new health. What this means is we are copying whatever value is in new health to the return variable, if you think of it that way. You can totally think of it that way. So you can think of, that's why you have int here, think of that as a variable on its own. It just doesn't have a name. Or it doesn't,
where in this example, where is new health going?
So new health is created here.
No, sorry, the return of new health.
To whomever is calling the function.
Okay.
Yeah. And we'll see that in a bit as well.
Okay.
So think of this as you're copying new health to the return variable.
And what is take damage considered again? That's just the function.
That's just the name of the function.
Okay.
Yeah. So it's what it's called. If you want to use it, you call it that way.
Yeah.
And then the question is, how much memory do they take? So an int is 4 bytes.
Okay.
So you'd think, yeah, it's 4 times 4 bytes.
Yeah.
Yeah. And that's correct.
Okay.
Okay. And we talked about this. Yeah. What is the variable that is returned? And it is an int. It doesn't have a name, but we can use it. That's why we have the return statement. So this return new health is to saying what value should be in the return variable. It is the value of new health. All right. And then how big is it?
16 bytes.
So total is 16 bytes.
Oh, it's only 4 bytes though.
And then it's 4 bytes for the end. Great. Okay. So we have the return value. We can think of that as a block of memory, which is the 4 bytes. And then we have the damage value, then the health value, and then new health when we're in the function, right? And they're all 4 bytes each. Great. So there's something happening here where we are creating these boxes of memory. Like you can think of each box as 4 bytes of RAM, if we think about it that way. So we say when we create or when we call the take damage function, we say we need 4 bytes for the return value. We need 4 bytes for the damage value that someone is going to give us. We need 4 bytes for the health value. And then when we're inside of the function, we need 4 bytes for the new health variable. Those are all the variables that we have. And it's good to think about the code in that way because this is called the stack.
Okay.
You can see that we're stacking on top of each other or below each other each one of the variables.
What is a stack overflow?
Yes, that's when you keep adding to the stack and you don't remove from it because the stack only has, when you create an application, the operating system says, oh, this application can have 1 megabyte of stack, let's say. And then you keep adding to the stack without removing from it.
So it's just it'll hit that cap eventually.
Yeah.
You're basically saying you're overflowing it.
Yeah.
I just ask because I've heard people say that stack overflow.
Yeah. So if you would say that allowable stack is like this, and then what we're doing now is calling the function, we're using a bit of the stack. and then we keep using. And if we keep using the stack without freeing from the stack, then when we ask for more, we can't, because we've used all of it. The operating system only gave us a meg or whatever.
What does that look like in terms of like? What would that look like if I open a program or something was running?
It wouldn't look like anything.
Okay, it just wouldn't behave different, or it just wouldn't do something.
Yeah, it wouldn't do a thing that you wanted, and then it would crash.
Oh, okay, so crash.
Yeah, it would, because it would want more memory, and the operating system says there is no more memory. Yeah. So the only way to handle that case is just say no when you crash. Because where are you going to go?
PC crash or the program?
Program.
Okay.
Yeah, that's one of the jobs of the operating system, is to trying to keep the PC running, even though if a program is misbehaving.
Just the daycare center, like, teacher. Yeah, stay in line. Stop it. You know.
You can totally think of the operating system as kind of the teacher, because you don't know what's going to be running. You don't know how things might behave or misbehave or whatever. Okay. So it's important that you think of the stack in this way, that you keep adding to it. What will then happen is, like, we've added the return, the damage value, the health value, and the new health onto the stack. And then when the function is over, because we talked about scope, that's why I introduced scope so early, is that when this function exits, it's done, then new health isn't needed anymore, right? So then this one here, this box here, will be removed from the stack, because we don't need it anymore.
Because the function stack will underflow.
Well, it's called popping from the stack.
Okay.
Yeah. And then, because the function is exiting, we don't need the health and the damage value anymore. So those two are also popped from the stack, because these arguments here aren't needed. And now the thing we have left is the return value, which we can then copy to whoever wanted it. And then when that copying is done, we can then pop the return value off. Technically, it's kind of not like that, but I want to introduce it to you this way, as a way of thinking about how this works. So if you think about it as, you put stuff on the stack, you use it, and then when the function is over, you pop them from the stack, and then the return value is given to the caller. So I want you to think about it that way, even though operating system or CPU level wise, it's technically a little bit different, because you often don't use variables directly like this. You use registers on the CPU. But please think about it this way, because it's a nice mental model to think about how things work. Okay. But then the question comes, where do the arguments come from? Like, who? Because we always talked about sending them into the function. So if everything is made like this, like a stack, then where do they come from? Right?
As in, like, where does the health value come from?
Yeah, because we've seen in the code where, like, you have someone that's calling a function, and then they put those arguments in, and then we jump to the function, and then suddenly they're there, right? Teleported up to that location. So where do they come from?
The user input?
Yeah. Who put them there? That's, well, whatever code was using the stack before you. So before we went into this function, someone else was using the stack. Because there's this...
Get out of my function.
Yeah. So for whatever thread you're using, so there's a stack per thread, if you think of it that way. And since we're dealing with single-threaded code, we just have one stack. Before our function, the take damage function, before that function came to life, if you think of it that way, someone was using the stack, which is the code before you. So when that code was calling the function, they prepared the stack to put the arguments there. They said, like, hey, this function here needs these two arguments, so let's put them there and then call the function. So when the function is called, the top two things on the stack are the arguments you need.
But how do they know that those are the ones we need?
They trust that someone did that. Yeah. So if we have...
but wouldn't that be like, if I open my calculator
mm-hmm.
and I put a number in, isn't that me sending information
yes.
to some sort of variable value?
Yes.
So they wouldn't have known that I would have put the number 8 in unless they can see the future.
No, but they know that you're sending a number.
Ah.
Yeah.
What if I just start by dividing?
I don't know.
Divide by 0.
Nah, exactly. Okay. So let's think of an example like this. We have a function called combat, and we create health and damage. In this case, it's 150. Doesn't matter much. Then ... we do some work. And then at some point...
That's not how it works.
Yes.
Can I code like this?
Sure.
I'll turn in my homework and just put something in ...
And then magic.
Yeah.
Gay Potter wants to break the code.
Break things.
Yeah. So we create health and damage in some way, ... and then we call take damage. And then you see also that the result of take damage goes into a variable called result. It's called it the same. But you can see that on line 16 that the combat function is calling the take damage function. So that is the caller, and take damage is the callee. So take damage needs those two arguments, health and damage, to be there. And in line 16, the combat function is calling it by putting health and damage in.
Yeah, so we're assigning health and damage to be 100. And then we're creating a whole, but then we create result, and the result runs the take damage function.
Result gets from the return value.
Yeah, so basically it would be 11 and 12 assign the values. 16 runs to get the result, but doesn't know the result yet, so it jumps back up to 1.
Yep.
And then it does that, and then comes back to 16, and then you have your result.
Exactly.
Okay.
Exactly. Gabe, I'm proud of that.
Trying to figure it out.
That was really good. That was a moment. That was a really good moment.
Was it a moment?
It was a moment. I like that. Because that showed that, because code isn't read like books.
But where does this technically start? Because
whoever calls combat.
Okay, so it would start at 9.
Yeah.
Okay.
Yeah, and combat might be called from main, and then you might say who called main, and that answer is the operating system, and then you say who started
who called the operating system. Then we're getting into philosophical questions.
Yeah. So
who created the world?
Exactly. Okay, so let's say we have this example. So we have some combat, it calls take damage and goes back up. Great. So let's visualize this. So here's the stack. So on the stack we have health and damage. It's 150. Great. And I've kind of also tried to highlight I don't know how well it is visible.
It's pretty good.
Pretty good. So now this is the stack. Then we want to call the function. So what we do, so I want you to think about it this way, even though it's often optimized to be a little quicker or not this way, but I want you to think about it this way, that we align those two arguments up. We say argument 1, we put 100 in it. Argument 2, we put a 50 in it. So even though you see that you might be duplicating data, there's a difference between sending something into a function and then the other variables on the stack. So here's the idea that we're lining things up for the call. So we say argument 1 is 100, argument 2 is 50. Then we call take damage, and now look what's on the stack above us. 50 and 100, which is the health and the damage that we need.
Yeah.
So when we were called, above us on the stack are the two arguments that we need.
But now it's duplicating.
Well, it's only duplicating in this case, in this example, because we could have created health and damage. We could have created other variables on the stack. We could have created a bunch of stuff, like where the player is, the XY coordinates, blah, blah, blah. And then we call the function. So that's why we need to put them there. So in this example, we're duplicating things, but it only looks like that in this case. So the important bit is look at it from this case that when we call take damage is a function that takes in 2 ints. That means that we need the 2 ints. Where are they? They're above us. They're right there. We can pluck them down.
Come here.
Yeah. And it was here. It was before I was even called, because whoever generated the code for it said like, oh, we're going to call this function over here. What does this function need? This function needs 2 arguments. Those 2 arguments are int. What are their values? For health, it's 100. For damage, it's 50.
But this would be someone who's assigned these values knowing that this is always the same values. Because these would be like hard-coded in, right?
No. Like getting the 100 and getting the 50 wouldn't be done at compile time. It would be done while you're running the program.
Okay.
Yeah. So you would say, like for the first argument, what do we need? It's called health. What is the value of health? It's 100. Let's put 100 in for the first argument. Second argument, what is the value? It's 50. Let's put 50 there. So that is, you can think of that as the preparation before you call the function. And then you call it, the function looks up and says like, there they are. Those are the two values I need. He plugs them down, does the code, runs the code or whatever it wants to do, fills in the return value with the results, would be health minus damage, so ended up at 50. And then what would happen is it will be popped out. And now results have the 50. So you can see that even though, so we grew the stack, we're growing the stack, now the function is done, pop.
But then I guess while the stack is growing, you also need to take into account all the things that will pop in and out.
Yes.
So you have to have like a buffer of...
That's why the stack is about a meg or two, or depending on the operating system, or you can make it bigger. So we're talking about 4 bytes over here.
Yeah. So
it's not that much, but there's other stuff that's going on the stack. But as a visual representation of what's going on, this is what's going on. Okay. Any questions so far?
I mean...
But yeah.
No.
Okay. But yeah, this is the important bit of, because it's been this kind of a mystique of where does the result come from? How does the return go into result? How does the arguments go into the function? And this is how. Think of it like this: someone prepared it, we call, it's there, we use it, we calculate, we have the return value, we pop it off, and there we go. Because then it's the same thing with combat. In line 16, combat is expecting the return value to be somewhere. It's expecting that take damage also behaves well, does its thing, and puts the value in the correct spot, which it does. It returns it. Because then it can just copy it from there. Because it's saying, like, where should it be? It should be in the box marked for return value. That means that I can just copy it from there. And then we get it there. Okay? Yeah, it takes a while to sink in. But if you have this mental image of preparation, adding and removing from the stack, and then popping from the stack, then that will help. Cool. So great. So this is called stack-based memory allocation. You have a stack, you add to it, you remove to it. Okay. But yeah, stack values, you stack values on top of each other or below. You can think of it either way. So technically they are added below. So the stack grows down in actuality, but you can think about it as stacking up, stacking down, doesn't matter much. And when you're done, you pop them off the stack. So stack overflow is when you keep adding. You don't pop. You just keep adding, keep adding.
But do you pop when you return a value?
Yep.
Okay, it's always on the return value, or is it other...
Any scope exit.
Okay. So
that's why, remember when we did the scope...
Wait, so one scope is a stack?
No.
Okay.
A scope says this only lives in this scope.
So yeah, so if it's void combat,
yeah,
you could call like 15 functions in there.
Yeah.
And that the void combat is the stack.
Yeah.
And everything in there is adding to that stack.
So there's only one stack.
Yeah.
But when here in void combat,
yeah,
when void combat exits on line 19,
yeah,
if we go
the stack goes back to that.
No, when void combat exits, result, damage, and health also pop from the stack.
Oh.
Because
so you can have empty stacks.
Oh yeah.
Oh okay.
Yeah, because
but technically when you start, I'm just thinking in terms of like
when you start, the stack is empty.
Yeah, and then how much can go into it is depending on how many functions and information and variables you add into the scope.
You got it.
And that can be like forever long.
As many as totally. So here on line 19, like let's say we got the result, we do some more, whatever. Now we're done. Here's line 19. Let's say that the stack looks like this when we're done, because we have int result that is created here. We have the health and damage. They're still alive. So here you can also see that why we needed to create the clones, because they're still alive after the function call. If they would also be, if they would use this, they wouldn't have anything to pop. So on line 19, result, damage, and health also pop. because then someone else who called combat
We'll
goes,
get a stack.
yeah, will get the stack and they'll do their thing. Yeah. Exactly, disadvantage to use as well. Well, I'm doing it for the example of showing adding onto the stack. So I mentioned that earlier. So this is called stack-based memory allocation. You stack values on top of each other, and when you're done, you pop them off the stack. And then stack grows and shrink based on usage. So this is the important bit. But there's a problem.
Uh-oh.
Yes. So if you look at the example, you always need to know how much of the stack you're going to use.
There's a lot of counting manually.
Well, if we look at this case again, like in this case here, if we call combat and then we call take damage does something, it's always the same. There's never any variability in how the stack is going to look. Well, what if in some cases we need like 100 items on the stack, and in some cases we need 5 items on the stack? If we need dynamic, this is very static. This is very fixed in that case. And when you compile the program, the compiler and the operating system, everybody knows that, oh, you're going to be needing roughly this amount of the stack. So you always need to know how much of the stack you're going to use. So, and this kind of needs to be known at compile time. So how do you ask for memory? How do you ask for dynamic memory?
Excuse me, memory. Can you please be dynamic?
Yeah, you can ask kindly. That can be a thing.
Hello.
Yeah.
I have no idea.
Like if, let's say that you have a gun, and gun can have X amount of bullets, and you want to store all the bullets somewhere. Well, you can't store them on the stack, because if you'd store them on the stack, they'd have to be alive. Like the number of bullets you need to know about, and the bullets themselves, they need to be known at all times. You don't want the scope to exit, and then suddenly you don't know how many bullets you have, or the actual bullets that you're using. Or let's say that you can have X many people on your team. You can have 4 people on your team. Well, how many people do you have now, or how many people do you need? Well, you can't put that on the stack, because if the scope exits to do something else,
It's all gone.
It's all gone, right? So there's a big problem here that the stack is only usable for certain things. All right. So, well, yeah, with the stack, you can't. I put an asterisk there because there are tricks. I'm not going to go into it, but if someone would ask, like, but hey, like, well, actually, there is like, no. For us,
cover your bases.
For us, you can't. Okay. So, but there is one way.
Oh.
There's one way that is usually used, that we use. What if you ask for memory, and that memory is just stored somewhere else? It's not on the stack. And then when you ask for the memory, you get the memory address of where it is in RAM. You just say, hey, can I
borrow this?
Can I get some RAM? And the operating system is like, yeah, sure. Here's the memory address. Be careful.
Go put your stuff over there.
Yeah. And then you save that memory address on the stack. You save it on the stack in a regular variable, and you know the size of that regular variable. So now you have some memory reserved somewhere else, and the stack is happy because the stack knows how everything is, and then you have a memory somewhere else. So it's the idea that you say, can I get 4 bytes, or can I get 1 megabyte? And the operating system will say, yep, you can have 1 megabyte or 4 bytes, or how much you need. And it will say, here is the memory address of where that bit of memory starts.
And then the stack can use that memory address?
Yeah, you save just the memory address. And memory address is, on 32-bit computers, is 32 bits. And on 64-bit computers is 64 bits. It's kind of simple that. And because you know how big a memory address is, you know how big the variable is needed to store the memory address. So the stack is happy because it knows how big it needs to store the memory address. Even though the stack doesn't know what is that.
What is over there?
No, it doesn't know that.
It just knows. So then technically, like if you created a stack with a function that had a bunch of variables, one of them could just be just sent to another memory address.
Yeah.
Where then it does the stuff. Does it like then do the stuff in that, or does it just grab it temporarily and use it, or like
do the stuff over there?
And then it just brings back a value.
Yeah.
Okay.
Okay. So let's look at this. So this is called a heap. So this kind of memory is called a heap. And the variable you store the memory address is called a pointer.
I've heard pointer before.
Yeah. So a pointer is a variable that stores memory addresses. That's the only thing it does. It's not magical in any way. It's like an int stores a number. An int pointer doesn't store an int. It stores a memory address of where if you go to that memory address, the int is there.
But then the program is deciding the memory address.
Yeah. What
is the programmer doing then?
He's saying I would like an integer somewhere. I'll show you an example in a bit. Yeah, it's called the pointer, and often pointers are shown as like an arrow. You'd have a box, which is the pointer. Then you'd have an arrow pointing to a box. There's no actual pointing happening. There's no arrows happening. The pointer is just a memory address. So think of it as the difference between, if you think of the stack or some memory as a house, the house is somewhere. It is physically, literally in some actual location, right? Be it the stack or the heap, doesn't matter. But then a pointer is an address. It's a representation of where this house is.
So you get like mail.
Yeah.
It says, please return to this address.
Exactly.
So it goes over to that address, goes, hello.
Yeah, and it takes a bit of time to go to the address, but when you're there you go. You're at the house. Doesn't matter if the house is on the stack or if the house is on the heap. Once you're there, great. If it's on the stack, it's usually quicker. But if you need dynamic memory, then it's you take some time to walk over there and then you're there. So don't think of pointers as anything like they are. It might take a while to get used to them, but they are much simpler than you might imagine. All right. So let's show some examples. So here I create a pointer variable on the stack.
Is the asterisk how you do that?
Yeah.
Okay.
So I'm saying that this is an int pointer. Think of it that way. The naming is the same. There's no difference here. You can name variables the same. But think of this, the int star, as the whole thing. So instead of saying int, like we did before, where you just create an int, you're saying it's an int star, which means it's a pointer to an int. If you read it, you can read it backwards. Some people do that. They say it's a pointer to an int. So this variable here, this variable health, it does not store the health. It stores the address of where the health is on the heap. Or in this case, it stores nothing because we haven't done anything.
Yeah.
So in the next section, we can say that health is equal to new int. And here you might recognize this from processing, where we did the new thing.
Yeah.
Yeah. This is kind of like that. But new in C++ asks the operating system for memory of size this. It asks for this much memory. So here we're asking for int size memory, we're asking for 4 bytes. And it will return where in memory that is. And then it will save that here. So again...
So it's... No, yeah, you continue. I'm just... So the new int is just telling you to give you the value back from the int that you sent in before to memory?
It's just asking for the memory on the heap, and it returns the address. So don't think about a number right now.
Yeah.
Just think in orders of memory addresses.
But so health equals new int.
Mm-hmm.
It's returned a memory address.
Yes.
But isn't a memory address way bigger than 4 bytes? Or is it returning the value from the memory address?
It's returning the value of the memory address.
Oh, okay. I thought it was just returning the memory address, which was 64.
Well, yeah, and if it's a 64-bit system, then an int pointer is 64 bits.
Yeah, but not on the new int. It's just returning the value.
It's returning the memory address. Just thinking in these two lines, just think in terms of memory addresses.
But the memory address, as you said, is 64-bit bytes.
64 bits. Mm-hmm. And an int star is 64 bits in size.
Yeah, but then when you return new int, you said it returns...
It returns a memory address.
Yeah.
And the size of a memory address is 64 bits.
Yeah.
It will be stored in health.
Yeah.
What we asked for on the heap is 4 bytes.
But we got way more than that.
We got well, no. Okay, no. So there's two things happening here. Okay, let's think of it as what's happening on the stack. On the stack, we're creating int star, which on 64-bit systems is and it's 8 bytes, if we think of it that way. Okay, and there's nothing stored there. It's an empty variable. Then we say health is equal to new int. And this will return us a memory address, which is 8 bytes. And we'll save that 8 bytes here. What this will also do is the memory address that we asked for can store 4 bits. The 4 bytes, well.
So the value of health.
The value of the memory that we asked for.
Yeah. Is stored in health, which is 4 bytes.
Yeah.
Okay.
There's a difference between how big the pointer is versus how big is the memory we asked for. We only asked for 4 bytes.
How do we know? Because now I'm like imagining that you go, hello, I'd like some paint because I'm going to paint my house. And they just bring you a truck of paint. But you're like, I only needed one thing.
Okay.
Because you're just asking for, give me this. How does it know exactly? Or you needed a truck of paint, but it's only giving you 1 can.
Yes.
Because it's...
No, think of it as well, it breaks a little bit in this analogy. Let's say that you bring the truck to the paint store.
Yeah.
And you say, I just need 1 paint can. And then you put the 1 paint can in your truck and you drive away. You're happy.
Yeah.
You go to the paint store and you say, I need 100 paint cans. You still have the truck.
Yeah.
And you can fit 100 paint cans in your truck. The analogy breaks a little bit there, but because you can, in this case, you can ask for 1 billion paint cans and it will still work.
Yeah.
It's a difference between, because if you think of it as 2 lines, even though it's not 2 lines, but think of it as 2 lines. 1 line is the stack, and the pointer is on the stack. And 1 line is the heap, and how much we asked for is on the heap.
Yeah, I'm curious about if I just ask for new int, so I want 4 bytes of information.
Yep.
How does it know if that is grabbing the right 4 bytes?
It just wants 4 bytes somewhere. It doesn't care where.
But it's asking for a value.
No, it's asking for a slot of memory.
Oh.
It's just saying, can I have 4 bytes of space somewhere?
Okay, because I was about to use the mouse to be like, doesn't make sense. So I was reading it as int health, the int asterisk health, which is sending now pointing to a memory address, which is 64 bytes. Well, it doesn't matter. It's pointing to a memory address. But then we create health new int. But when we say new int, we're also going, I need a memory address with 4 bytes.
Yeah. So this one just makes a point, says like there's a pointer somewhere.
Yeah. But is it asking for 4 bytes within the memory address that we already assigned? I was reading it as, so in my head it was, we get this memory address, then we create health new int. New int is pulling in the value from that memory address.
It's pulling where the slot is. It's saying like, I want to build a house.
Yeah.
You're asking the government, I would like to build a house. And the government says, there's an empty slot on Johnson Street. On Johnson Street number 4. And then you get written down Johnson Street number 4, and then you have that as a paper. That's the pointer.
Yeah.
Now you can go to Johnson Street number 4 and build your house.
Yeah.
You can also go to the government and say, I would like to build a mall. And then they would say, there's an empty slot on Johnson Street number 5. and then you take that address and you go to Johnson Street number 5 and you build your mall. You notice the difference between that. The address they wrote on the piece of paper is the same size in both cases.
Yeah.
If someone says, I would like to build one house, there's an empty slot on Johnson Street number 4. Johnson Street number 4, here's the paper, go and build your house. And if I say, I want to build a mall, there's an empty slot on Johnson Street number 5, then you go build a mall. Just because there's an empty slot there. The address that's written on the piece of paper is the same size. Even though
it's just ask. So when we have health equals new int,
yes,
it's saying just in that memory address, or in that, like, if we're saying, oh, I want to build something smaller that goes to the side of this house.
Yeah.
Like, I want to build a garden.
Yeah.
That's the int.
Yeah.
But it's still the same address, but we want to ask for something specific, or we want to ask it to reserve some amount of information in that.
That one.
Okay.
Yeah. Because you say, the address written on the piece of paper, that's the pointer.
Yeah.
That's always the same size.
Yeah.
But how much is over there, how much space is over there, that is on this part, the new...
Okay, yeah. So it's like, I want to build a house, but reserve space for a garden.
Yes.
Which is the new int.
Yeah.
Which is a part of the whole available space. Because
Yes.
it's like a lot, and you have a backyard.
There we go.
And then you say, I want a new int, which is a garden.
Yeah, because you could then say, like, you could say something star.
Yeah.
And let's call that health. And you say health is equal to new something really big. The address is still the same.
Yeah.
Address size doesn't change. Because address is always the same. But you asked for a big lot of space.
Yeah. And then you can do whatever you want in there, as long as you can put as much stuff as you want until it fills up.
You got it.
Okay.
You got it.
Wow, that went everywhere in my head.
No,
I was like,
that's what I'm saying.
What?
No, this is a topic that takes some people quite a while to get used to, because it is this disconnect.
Yeah.
It's these two worlds that are jumping back and forth. But if you get this important bit that pointers just have addresses in them.
So when you have, are you gonna have an example of like a bigger section of code?
I have a little bit more below. How you use it?
Because I'm just curious, like, what this actually looks like in practice. Because I would get so confused if int health was its own thing, int asterisk health, and then below it's just health new int, and it's not connected to int, or is it all within one scope?
So this is in one scope.
Yeah.
So you can say int star health, like any other variable. You can say health is new int, like any other variable.
Yeah.
But the difference is that when the scope exits, the pointer, because the pointer is on the stack, the guy who contains the address, he's on the stack. He's dead when the scope exits, but not the space. So if you say, you go to the government and say, I would like to build a house, and they say Johnson Street number 5, you say, cool, I have this piece of paper that tells me where I can build my house, and then you lose the piece of paper. Right?
No.
They've allocated and said, like, no, Gabe is going to build a house on Johnson Street number 5. And you're like, I don't know where it was. I'm lost. Right?
Yeah.
Yeah. So let's continue. So if you would like to build your house, or if you would like to store something, the int, or you'd like to store a value, because remember before, if this was just an int, we didn't have to do the whole new thing, and we didn't have to say star before it. We just had to say health is equal to 50, right? But since it's a pointer, you have to dereference, it's called. You have to, if you have the piece of paper and you want to build a house, you can't build the house on the piece of paper. You have to go to the place where the house is and then build the house. So you have to go to the heap and then put the value. So you need to say star health. You'd say wherever the int is, somewhere in RAM, put 50.
Okay.
Yeah. But then the important bit is, when you're done, when you said, I've built my house, I've lived in it for years and years, I'm not done, you need to delete it.
Oh, no.
You need to say, delete
demolish.
Health.
Okay.
No, not necessarily demolish, no. What this is, I don't need that space anymore. You go to the government and you say, hey, I did something in that slot on Johnson Street number 5, I'm done. You can do whatever you want with that. You can demolish it. You can keep it. Have fun.
Turn it into a museum.
Yeah, I'm done. Because the important bit is, let's say that the scope would exit here on live 12. Let's say the scope started here on line 1, we did our thing, and then scope exit on line 12. We can't say delete health because the scope exit. So this here is dead. So we can't say delete health. Oh, and this is called a dangling pointer.
Ah.
And this is called a memory leak.
Oh, no.
Yes.
So you always have to delete it when you're done?
Yes. And here's the thing. I'm teaching you this, I'm showing you this, and next week we'll do a little bit of exercise with this. The cool thing is now with C++, you don't need to do this anymore. But you need to know about this.
Do it, does the compiler do it automatically or whatever?
No, like there are new. So there are things. So this is a pointer, and this is usually called a raw pointer.
Yeah. Because
you do everything yourself. It's very raw in that sense. There are smart pointers now out that will delete themselves.
Yay!
Yeah, they will do all the cleanup for you. So that's.
Is there ever a case where you want a memory leak?
No.
Okay, it's like I'm trying to think of like.
No.
Because this is basically what happens if like you're playing a game and it slowly is eating more and more memory.
Yep.
Okay. They just haven't deleted.
Yeah.
Now every time I have a game with a memory leak, I'm gonna tweet at them and be like, "Delete your stack."
Delete your pointers.
To pointers.
There you go.
Don't delete your stack. You need those.
You need your stack.
Delete your pointers.
Yeah. So the stack is still there, and the stack is still very, very important. Like the pointer itself, not like you keep the paper with the memory address on the stack. That's still there, but the location of where it is, that is somewhere else, and you need to let someone know when you're done. So the stack is very important. The stack is still used. That's why I'm teaching the fundamentals initially like this.
Praise be to the stack.
Because the stack is still used, and the stack, you can use a lot of things for the stack. But the important thing here is you could then create some memory. You can make a function that says like, hey, I'm gonna create a pointer. I'm gonna allocate some stuff on the heap. I'm gonna put in some values. I'm gonna then return the pointer from the function. And now someone gets the pointer and the value is still alive. I have a pointer now and the value is still alive, and I can just pass that pointer around to all of the people. So if it is the bullets in the gun or the people in the party you're playing with, someone made that on the heap, made a pointer to it, and then passed that pointer around, and that thing is still alive in memory while the group or the bullets or whatever is still there. And then when you're done, when you're loading a new level or whatever, boop, then you clean everything. So that's the important bit. That's why this is used, is that you can create memory, put stuff into it, and then keep it alive until you decide we don't need it anymore. It's not dictated by the stack, it's not dictated by the scope, it's still there.
And the speed at which you're going from memory to stacks or pointers and in stacks and popping is like...
So adding to a stack and popping from a stack is very fast. Creating this, here line 6, this can take time. This can be slow.
What is time?
We're still in the like nanosecond, microsecond case,
okay.
But it adds up. It totally adds up. And so this here, line 6, this takes time. Line 2 doesn't take time. And I believe on most operating systems, line 17 doesn't take time either. Line 6 takes time, and line 11 takes time as well. Like line 11 is more expensive with the star than without the star. Mm-hmm. And a thing that people who are beginning to play with pointers is that a big mistake that they would do is they would say this. They would say int star health. Health is equal to new int. And then they would say health is equal to 50. They wouldn't put the star. Because what health was storing was the memory address. You're saying the new memory address is 50. We're gonna work with memory address number 50, not go to memory address and put 50 there. So instead of building your house in the location of where it should be built, you built the house on the piece of paper. So it's important to go to...
I'd be impressed if you built a house on a piece of paper. Though,
maybe you could put a garden there, I don't know. But if we continue that analogy, which I think it works well.
Just gonna keep going.
Mm-hmm. So that is kind of like a beginner's, but you'll see that your program will crash if that happens. Yeah, you
can't build a house on paper. It turns out.
Yeah, you can't play with memory address number 50. That's like way too low. That's like operating system level memory addresses. Like you're in the millions usually. Okay, so that's what I had today. The important bit is to know about this stack and heap. Stop trolling.
No, I need the USB on my desk to transfer the video file. I forgot about it.
So, like I said before, there's no homework this week because we will continue with this next week. We'll play. Next week is less lecture, more practical. We'll play with pointers a little bit because we need to know that this exists and how this works. But then I'll also show you smart pointers and how they work.
Fantastic.
And then the week after, we'll look at like general data containers. Because once you learn about smart pointers and how they work, you can actually transition into data containers, or like dynamic containers. Because you could then say, I want a big list of players, which is also another way of allocating memory. And you do it dynamically. And there's a bunch of like caveats that might be surprising there as well. All right.
Cool.
Cool.
Yeah, that's this week. We'll be back next week, same time, so 2:00 CET, Central European Time, right here. VOD will be out. I mean, if you're watching the VOD, then clearly it's out. If you didn't catch the whole stream, VOD will be out on Monday. But otherwise, we'll see you next time. Stay smart.